Our next speaker is Antti Aronen. He's an engineer at Glaston for the thermal tempering process, has been there for a while. He also has about 10 years experience in vacuum insulated glazing, and today he'll be talking about an enhanced model for predicting thermal performance in a vacuum glazing. So please, a warm welcome for Antti.
Thank you. So let's start. As Senk mentioned, now I'm working at Glaston, working more with the heat-driven processes like tempering, lamination, screen painting, and things like that. But a little bit over 5 years ago, I was working with the Senk at the University of Sydney, and there we did some research also about thermal stresses in vacuum insulated glazing and how we can solve those analytically. So that's my topic, to tell you some examples and equations how we can solve thermo-mechanical loadings in vacuum insulated glazing. And so we think this kind of solution we can quite efficiently estimate the stresses and deformations in vacuum insulated glazing. Maybe here's someone who hasn't never seen vacuum insulated glazing. A couple of words about that. So idea is that there is two panes, and there is a gap between those two panes. There needs to be some pillars to keep this gap there, while edges are hermetically sealed together, and then vacuum is done between those two glasses. So the idea is the same than in ICUs, to put the two glasses and gap between and increase the U value. In this case, there is in this gap there is no air. There is just the vacuum, so that to increase the insulation properties of that glass. But there are some problems which are coming when these glasses or glass panes are at the different temperatures. Glasses start to bend, and that causes stresses in a glass. So I'm going to show to you that man, it looks awful. That this thermomechanical model gives a good result for deformation and stresses for simplified cases of VHC. So here's a couple of things what we see when one glass pane of VHC is expanding due to a hot or warmer temperature, and another one is shrinking when it's colder than another one. So hotter one tries to expand, and the colder one tries to shrink. And however, there is the edge seal which prevents this relative movement, and that's causing forces in the pane. And forces cause stresses or bending, and the result is that there are stresses and bending, but those are depending on the different edge constraints. So I'm going to show you a couple of different edge constraint cases what we have been studied. Some equations, I know that you all love these ones, but basic equation for stresses. There are some external moments and the thermal part. The main thing in this presentation is to focus in the thermal part. So there is coming a thermal force and thermal bending. And then there is also expansion what is coming, or shrinking what is coming from temperature change, which also affects in the stresses. Here are some equations how those normal stress and bending the thermal effect is are calculated. But in this equation, also external forces are in big role. And that depends on what kind of edge constraints you have in your system, where you have installed this vacuum insulated glazing. And because of thermal moment, you can also get bending, so that, as I told before, hotter one tries to expand, and colder one tries to shrink, and that causes bending. And this curvature, what you get for the glass, depends on this thermal moment and also moment from external forces. And then you can calculate what kind of deformation or shape you will get. Example about case where you have same thickness glasses. Cases like this. There are two panes to get combined together from the edge, and those are at a different temperature. And at the edge there is a middle temperature from those two panes. If we have a free case, there is no external forces, so those can be taken off. And because we have the same thickness in both panes, there is no normal thermal stress at all. So all the stresses what we get in this case are related to a thermal bending due to a moment, and what is effect of this temperature change in individual pane. Edge stresses are a little bit simplified from this one. You can take this one off because stresses in this case to x direction at the edge are 0. And here are some results for that. I hope you see. It's not too low. So if we are looking at first this part, this one is causing suspending. So it will cause linear stress distribution in glass. But because we have also this parameter here, you get both panes, set of stress distribution gets a little bit shift based on this value. So over each pane, you get different kind of stresses, and in this case, extreme case is in the middle surface of the VIC over this gap. But and then edge stresses are shown with those gray dots, and along its line there should be linear change over those stresses. If we change the case for the case where there is thicknesses for those panes are different, results change. And there are equations how you easily can solve stresses for free case. There is again same linear change to a thickness, but the shifting is different. And we have also compared these analytical results to finite element results. There is some information what we have done. Glass size has been just 350 by 500 millimeters. Glass thickness is 4 millimeter and 6 millimeter. Temperature difference only 10 centigrades. And in analytical solution, we are not taking this gap in consider. We notice that it has a slight effect in the total results, so making everything easier for analytical solutions, we took that one off so that the internal surfaces are connected to each other in our model. But however, to compare how it works with the finite element, there is gap, there are pillars, and everything is taken in consider in the finite element calculations. But in these first cases, we use same temperatures, uniform temperatures in both cases, so that it's kind of extreme case where you have really high heat transfer coefficient on a glass surface. And if we are looking at results for that, here are with the dots, analytical solutions, and with lines, those finite element solutions. And it shows stresses in different surfaces. So the black one is surface 1, which goes outside the temperature, and then surface 2, red, surface 3, green, and surface 4 is as orange. So, as you can see, these stresses with analytical solution and finite element solution are about same when you are going to the middle of the glass, but at the edge there is some slight changes in those results. And same thing with the deformation. When we are starting from the corner, going to center of the glass, the analytical solutions gives a little bit higher bending. It's a little bit stiffer maybe because of in the finite element there is also this gap included. So as a result from those ones, we see that analytical solution gives good results for freely supported cases. So we can quite easily estimate what kind of stresses you should get in the middle area of the glass, and also a little bit for that what should be stresses at the edges of the glass. Then we expanded this model to a simply supported and fixed case. There are coming some extra things what has to be solved. It's not that simple anymore. It's a little bit more complex. So if we are looking at equations, main equations are same, but they are coming also boundary conditions, which gives external moment or external forces. In this case, mainly just external moments to the edges. But the solution we had to solve with the trigonometric series solution. So for deformation, we use one equation with the specific terms for that, and for thermal moment, same kind of trigonometric series with the different constants. And in this case, if we go simply supported or fixed cases, depending on what kind of constraints you have, you get a little bit different kind of moments and the deformation equation at the end. At first, the equations for simply supported case, it needs a quite simple series solution, but and same thing for the external moments. Maybe you know what simply supported means. So there is a plane, and it's supported so that it's always touched to this its frame, but it can bend from the edge. If we look at results, outer surfaces on cold side, hot side, dots are again analytical solutions, lines are finite element solutions. You can see that the dots and lines are matching quite well. But if we are going to an internal surface, then most likely due to this gap, stresses are a little bit up for normal stresses between those analytical and finite element solutions. If we go to a fixed case, solutions are a little bit more complex. They are coming because of boundary conditions, extra terms in deformation, and also similar kind of terms in external moments. In a fixed case, the case is a little bit different than a simply supported. Now the glass pane is going to be fixed in a frame so that it can't bend from the edge. It needs to be bended from more far away from the edge. Say if something is bending from that pane. And if we are looking at results now, you see that top ones are on surface 1 and 2, so that's a coated pane, and stresses on the both side surface of that coated pane are same. So that means that there is not really bending, it's just flat case, and all the stresses are coming because of temperature change. Same thing for hot pane. Stresses on the outer surface of outer and inner surface of the hot pane, those are more or less same, so there is no bending in the glass, but the stresses in the middle of the glass area are working really well. There might be some differences at the edge area because in the finite element there are a little bit different things, but how it all combines compared to an analytical model, because in the analytical model you can take everything in consider. But stresses in the middle are in a good range between finite element and analytical solution. And deformations, this free case I showed before. For simply supported case results matching really well. And for fixed case, you see that there is no deformation when you get good fixed solution. But the problem is that when you have real case, your support is usually somewhere between these ones. So you can, with analytical solutions, you can only get extreme cases, either fully fixed or simply supported case. Something in between is difficult for analytical solution, but with finite element it's easier. But in that case also it's difficult to find what's really the right support from the edge or edge constraint. So as a result for this one, we see that the analytical solution gives good results with the different boundary conditions, so not only free case but also simply supported and fixed. There are some small differences which are coming, but those kind of giving extreme results, those analytical solutions. And then I have a couple more results where we have compared these uniform temperature cases, which are kind of worst case scenarios, to compare it with the non-uniform glass temperatures. So this means that we have, instead of having a constant temperature on surface of glass panes, we are having also heat transfer coefficient included. So that means that instead of we had in previous cases constant temperature, we can now temperature profile which is getting closer to average edge temperature at the edge. And also, because of heat transfer coefficients, this glass temperature in the middle of the glass is also a little bit smaller than before. But otherwise, analytical solutions were same, and there are some information about the case what we have used. And now, with red color, I have tried to show you what happens when we include this non-uniformity in temperatures. Like in the surveys 1 for free case, stresses are getting a little bit closer to 0. So that means that when we have uniform temperatures, we have extreme case, and also this analytical solution gives results for extreme case. There are also other surfaces, other stresses. If we go to simply supported, same thing again. There are some slight changes, say in shear stress, say for free and fixed case, but like in here, so that you can see that in a uniform tensor case, says shear stresses were 0, but now we get small shear stresses in this non-uniform temperature profile. And the bending is now less because temperature difference is smaller. And if we look at the fixed case, you can see that in any case it's small. We are talking about 100 times smaller deformations than with the free case. So that's not really a problem if we are thinking about designing the VHC solution for different case. So our results about this is that analog solution works well, and it gives a worst case outcome, except with some small differences at the shear stress. And altogether, we see that these results are a simple way, cost-effective way to resolve stresses and deformations in VHC. Thank you.